All right, welcome back to Factorising Polynomials. So by now you should know that polynomials is just the term we use for a equation in this form here. It can have any powers, there are certain rules around the powers, but if the highest power is generally written at the front, second highest, third highest is constant, so on down. It can have any power you'd like it, so long as they follow the rules, right? So this is just polynomial form. It doesn't really help you too much. As you know, when you graph things in this form, that's the y-intercept, that's the dilation, and everything else is just useless information. So we're going to look at how to convert polynomials in general into different forms. All right, so your first thing is going to be around factorizing them so you can find the x-intercepts, which you should hopefully remember from quadratics. Okay, so what we're going to look at is two rules today, the first of which is called the remainder theorem, and the second of which is called the factor theorem. Remainder theorem and factor theorem. And these are basically the same thing, just said different ways. All right, so for the remainder theorem, I'm going to demonstrate what this theorem is all about using long division. So we're going to long divide this polynomial by x minus 2. All right, so first step, x cubed divided by x is x squared. Multiply back down. X squared minus 2 is minus 2x squared. Subtract those. So I end up with 5x squared. Drop the next one down here. 5x squared divided by x gives us 5x. Multiply back down here. This should give us minus 10x. Subtract both of those. This should give us 12x plus 1. 12x divided by x is 12. So these should be pluses here, shouldn't they? Multiply back down, you get 12x minus 24. Subtract both of those. I end up with 25 and nothing left to divide. So this is the remainder. All right. Now the remainder theorem tells us something very interesting. It tells us that if I'd done this, which you might notice is just the actual x-intercept of x minus 2, all right? If I'd substituted 2 into the polynomial, I would have got, hold on, I'll put it actually in, 2 cubed plus 3, 2 squared plus 2, 2 plus 1. 2 cubed is 8, 2 squared is 4 times 3 is 12, 2 times 2 is 4 plus 1 equals 8 and 12 make 20, 4 and 1 make 5, so the answer is 25. So this is where remainder theorem has its strength. It says that long dividing a factor gives you the same remainder as just subdividing the x-intercept into the, substituting the x-intercept into the polynomial. So this is very helpful. This allows us to find x-intercepts of polynomials without actually doing any long division. We can just substitute values in until the remainder is 0, which leads us into the second thing of the factor theorem. And the factor theorem says that if the remainder equals 0, then that number is a factor. All right, so I'll bring you back to a rather simple example of 25 divided by 5. If 5 goes into 25 without a remainder, which it does, then I know that that number is a factor of that number. So if I can substitute if I can divide x minus 2 into this polynomial, end up with no remainder, then I know that that is a factor of this polynomial. So this remainder theorem is basically a shortcut to finding all the factors in the factor theorem. So the way to factorize this polynomial here would be to substitute values into it and check if there is a remainder. All right, so this opens up a whole quick way of doing things. And for those who are wondering about for what reason you would define a polynomial on your calculator, this is one of those reasons. You can define it as p and then just substitute x values in until this answer is 0. All right, instead of having to divide or something like that, or just guess, you can just quickly have the calculator do all your work for you. For the rest of the video, it goes for quite a while, but it deals with each of the different examples in questions 1, 3, 5, and 7. So if you go through the set and then revisit the video as you need help, that might be the best way rather than watching the full 20-minute video now and getting a bit bored. Alright, so in this example it just says to use the remainder theorem to find the value of the remainder when, here's your polynomial, and it's divided by x minus 2. So all you really have to do is 1, ID the factor, 2, sub it in, and 3, record outcome. All right, so this first one is going to be, the factor is 2, because the way you do it is you have to identify what x equals. So x equals 2. Then you would sub it in place of x, and it would be 2 cubed minus 3, 2 squared plus 2, 2 plus 6 is equal to 8 minus 2 squared is 4 times 3 is 12 plus 4 plus 6. So they make 10. That makes minus 4, so it equals 6. All right. 8 minus 12 is minus 4. Yep, 6. So the remainder, when this polynomial is divided by x minus 2, is going to be 6. And if you'd like to go and check that with a long division, by all means, go ahead. All right. Second one is fairly similar, but this is the key step here. You have to make sure you find the actual x value. So in this case, it's 2x plus 1 equals 0. So x is going to equal minus a half. All right. So you have to substitute minus a half into the polynomial. So minus a half cubed minus 2 minus a half plus 4, which equals minus 1/8 plus 1 plus 4, which is going to equal, what's that? 4 7/8. And again, you can check it if you'd like, but it should be fairly simple. All right, so to recap, the remainder theorem says that when a value is substituted into the polynomial, the remainder is the same as when it's divided by that same factor. All right, so you can just substitute that number in, work out the value, and that's the remainder as when you divided by it. So there's no need to do all the long division steps. You can just go straight to remainder. All right, however, there is a place for long division, which I'll demonstrate in a few minutes. If you want to give this skill a go, go and do a question 1 in set 6C. I know these videos are quite long, so to break it up, it might be worthwhile going and trying that question now and coming back to the video when you get to a different question. All right, so this is the example that uses long division and has to use long division. All right, so this is a question that says, show that x plus 1 is a factor and hence find the other linear factors. So there are two parts to this. There's the show that and then the hence find. All right, so that part there, this part here. So show that means that I have to tell you or prove to you the information that you've already been told. So it says that x plus 1 is a factor. So this implies that substituting minus 1 in to the polynomial produces a remainder of 0. All right, so I have to show that that is actually the case. So it's going to be minus 1 cubed minus 4 minus 1 squared plus minus 1 plus 6 equals minus 1 minus 4 minus 1 plus 6, which is 0. So QED means that I've proven what you wanted me to. All right, so that's the show that part done. However, it doesn't actually help me factorize this polynomial. So the way to factorize is to take that information and say, okay, I know that x plus 1 is a factor, so that's going to be my divisor. and I know that this is the polynomial that I'm dividing, and so I need to find out what the polynomial up here is before I can factorize all of it. All right, so let's do the division. So I've got x cubed divided by x is x squared. Multiply it back down. Multiply the 1, x squared, subtract them. That will be a subtract. So that's minus 5x squared. Drop the next term down. That's going to become minus 5x. Multiply it back down, so that's become minus 5x squared minus 5x. Subtract, so that turns into that. There's a 6x, so that's going to become plus 6. Multiply back down, drop the next term down there. 6x plus 6, subtract it out, which turns into a minus, and that's a 0. So now, we already knew the remainder, but we didn't know this. And this is going to help us find the other factors of the polynomial. So one factor is x plus 1. The other factor is x squared minus 5x plus 6. We know that that's a quadratic, and we know how to factorize quadratics by sight. If we can, we must do this. So factors of 6 that add to make minus 5 are going to be minus 6 and positive 1. And then I have 3 distinct factors which will help me find the x-intercepts of this polynomial. And go back to the question, it says hence find the other linear factors. The word linear is very important here. The quadratic was a factor, but it was a quadratic factor. These 3 factors here are linear because there's no power on the x. All right, so the question started by asking us to show that, which was the remainder theorem. Then it asked us to find the other linear factors, which did involve long division, because we needed to know this quadratic at the top here, the quotient, when this polynomial was divided by this divisor. All right, we already knew the remainder was 0, so we knew it would work. What we didn't know was this, which helps us find the other linear factors. This example deals with question 3 in 6C, so go and give that a go now. I'm just going to show you how to do the remainder theorem on your Casio. So first thing I've done is I've defined my polynomial. Just going interactive define, and then typing in what I needed to. Now the next thing is I'm going to try and factorize it, but I don't know which factors to start with. You notice in the previous example they said show that this factor is indeed a factor, but this one just says factorize. So I need to have some ideas. Now, logical thinking would suggest that if a factor is going to leave no remainder of this polynomial, then that constant term has to be able to cancel itself out. All right, so your first port of call would be to substitute values in for x that are also factors of the constant. All right, so let's start by doing that. Oop, don't want to write up there. I want to write down here. So p bracket. Now, what's a coefficient of 6? I mean, sorry, no, a factor of 6. Let's go with 2. All right, minus 4. The remainder is not 0, so that's not going to work. So let's change that to, let's try 3. There's a remainder of 0. All right, so that at this point, I can stop and go to my long division. I know one factor, which is enough for me to divide it out, get an exact quotient, and factorize from there. If I wanted to, and it is achievable for cubics, but for higher powers, you could be sitting there for a very long time. If I wanted to, I could just keep going with this. I could go, okay, so 3 is a factor. What about minus 3? Nope, not minus 3. And I could look for all the other possible factors that will produce remainders of 0. All right, which, depending on how many factors there are in the polynomial, could take you a few minutes. It might not take you as long as you hoped if you chanced upon the right one straight away, which would be good, but it could take a while. So your best bet is to go with the one you know, then long divide it through and work out the quotient from there. All right, so we'll just store that up there and we'll keep going. All right, so we've just seen on the Casio that p at 3 equals 0, which means that x minus 3 is a factor. All right, so I'm going to long divide this through x cubed minus 2x squared minus 5x plus 6, x minus 3. So I'm going to long divide it through x cubed minus 3x squared, subtract. So this gives us x squared, which is going to give x up there, drop down the next term, multiply it back down, subtract, which is going to give us minus 2x plus 6, minus 2, multiply it back down, plus 6, subtract it out, which is going to be minus there, 0. There's our remainder of 0, but the important part we're missing was this quotient. So I know that this is the rest of the factors. Now, if I can factorize this, I will have completely factorized this polynomial. So factors of minus 2 that add to make 1 are clearly 2 and 1. It needs to be a positive 1, so there's a positive 2 minus 1, x, and my third factor I knew from x minus 3. All right, so you can see the benefit here of how the remainder theorem fits in with the factor theorem, and with long division allows us to jump straight to the factors of a polynomial. As I said earlier, you could easily sit there and plug in all the possible factors of the constant term just to find out which ones left a remainder of 0, and that would give you all of these three solutions up here. All right, but you can see that for simple ones it's relatively straightforward. For complex ones, it's there's a list of factors which could be as long as your arm and longer. So your chances of finding them get slimmer the higher powered a polynomial is. It might be worthwhile going and giving question 5 a go now to break up the video. Oh, not 12. Question 5 in 6C to break up the video, just to give yourself a bit of practice. Do one last example about one that is slightly more complex. So it says here, factorize px equals 3x cubed plus 8x squared plus 2x minus 5. So I'm just going to go back in my initial line here, and I'm going to change this x squared plus 2x minus 5. Should say done. All right. Now, notice that it calculated everything under that point because I defined px. So now let's look at the constant here, minus 5. The possible factors are minus 5 positive 5 or minus 1 positive 1. So let's try those. All right, so that didn't work. What about minus 1? Again, that didn't work. What about minus 5? That didn't work. What about positive 5? All right, so now you might wonder why I did it differently this time. I put them all on the same screen so we could see that the remainders of all of them are not 0. It's not working. So another option to consider, especially useful when you have a coefficient of the lead term, so this is the 3 in this case, is that you might need to divide out the 3. But we don't need to do it to all of them. We only need to know what the constant will look like. And you can see that the constant will look like 5 divided by 3. Or in fraction form, it'll be 5 over 3, written like this, 5 over 3. So now, knowing that that could be our factor that we're looking for, let's plug that in and see if that produces us what we need. So 5 over 3, ooh, not, let's try minus 5 over 3. Hey, and there's our 0. All right, so now at this point, what does that mean in terms of a factor? Well, I'll show you in the next little bit. All right, so I'll just put that over there, and we'll explore what this might mean in terms of factor. So previously, when I said that 2 was a factor, we knew that it had to be the opposite, like that. All right, so this is going to be x and 5/3. The opposite of minus is a plus. So this is our factor here. We've got our polynomial under there, but we haven't actually learnt how to treat fractions, and you can understand that they might make it quite complex. So a way around it is to multiply the 3 back off the bottom over 2 in front of the x. So this would become 3x plus 5, which is suddenly a lot easier to work with. All right, so, oops, x squared plus 2x squared minus 5. So pretty simply, you divide this, instead of dividing it by x, you now divide it by 3x. So this is going to become x squared. Multiplying it back down produces the same result. Multiplied into the 5 gives you 5x squared. Subtract them out and it gets 3x squared. All right, 3x squared divided by 3x gives you x. Multiply it back down, so you can see it's not making a huge difference. Oops, I didn't drop down the next term. Multiply it back down gives you plus 5x. Oh, that shouldn't be a square, should it? That should just be a 2. Minus, that gives you minus 3x. Get rid of that one too. So at this point, minus 3x divided by 3x is minus 1. Multiply back down, you get minus 3x. Drop that constant, drop that one, subtract, you can see there's your remainder of 0. Here is your quotient up the top, so we know one factor is 3x plus 5, remainder of 0 says that that is also the other factor. And then if you've just suddenly decided that you don't like factorising quadratics because you notice that factors of minus 1 that add to positive 1 are non-existent and you have to complete the square, welcome to the party. So this is going to factorise into 2 of the almost the same factors. So we'll have to complete the square for this one, which definitely adds to the process, all right? But there's nothing that can be done about it, unfortunately. So put the minus 1 out here, halve, so you get a half, square, so you get a quarter. So plus a quarter, minus a quarter. And we know that the first 3 terms will factorise like this. It's plus, sorry, because that number just drops into there. Minus 5/4, which is those 2 terms added together. Then I can square root both of those and jump them inside the bracket, so it becomes x plus a half minus root 5 over root 4, and x plus a half plus root 5 over root 4. Now I can simplify further by saying that x plus a half minus root 5 over 2 and x plus a half plus root 5 over 2. And then I notice that the denominators are the same, so I can actually create one fraction like so in each bracket like that, and then tack the third factor on at the start. So my 3 factors for this are a linear factor and then 2 linear factors that involve surds, which are not very nice at all. So through a process of, first of all, identifying one factor where the remainder is 0, then long dividing through, then factorising the remainder, I've been able to completely factorise the polynomial. This example is about question 7 in 6C, so go and give that a go now if you want to practice this.